I understand.
Odds are, if anyone says centrifugal or centrifugal,
Yeah,
they're wrong.
right.
Now, there is a correct way to use it. Just the way most people use it, it's wrong.
Yeah.
So, let me finish the derivation I started before, and then get into the difference, because there's a key thing that comes out of it. I mentioned it briefly last time, but there's a key thing that comes out of it that basically defines what centripetal means, and centrifugal is the other way.
Okay.
That's a vertical line right there, which we'll just establish is the j hat direction. Like I hat to the right, because I lack imagination. Those angles are supposed to be the same, so I'm going to attempt I'm going to go with it anyway. I'm labeling these angles here as phi. So the full angle is 2 phi. And for those who can't quite understand me through the mask, that is the spelling of the angle. We have a constant speed here. And the speed, as done when I was slinging that stuff about in class, the speed is tangent to the arc. So ideally, I would draw these arrows the exact same length. And again, that is tangent. We broke it up into components. Where this angle here is phi, this angle here is phi. So my initial velocity is v cosine theta I hat plus v sine theta j hat. And v final is v cosine theta I hat minus v sine theta j hat. Ultimately, I'm trying to find the acceleration, because so far we have dealt with acceleration that occurs because of change in speed. We're now going to deal with acceleration because of change in direction, because there is no change in speed here. The formula for acceleration, vector acceleration, is still the same. And so if I do Vf minus Vi, which is change over time, I end up with, well, my I components will cancel out, and I'm left with negative 2 V sine theta j hat divided by time. Oh, and there's a mistake on the board, which no one corrected me on.
Yeah, no, wait.
Pardon?
I was trying to find the mistake, because it didn't.
Should be phi instead of.
Yes, should be phi.
How did you get this negative 2 V sine j hat?
Doing final minus initial, so I have negative sine phi j hat minus V sine phi j hat.
Okay. And you're saying these two over here cancel out?
Yeah, to write it out slightly more formally, we have V cosine phi I hat minus V sine phi j hat, that's V final, minus V cosine phi I hat plus V sine phi j hat, that's V initial. Distribute the minus sign, and we get V cosine I hat, negative V cosine I hat, negative V sine j hat, minus V sine j hat. Is that sufficient?
Yeah, thanks.
All right, so we're now left with this as the acceleration, which really doesn't help us a whole lot because, you know, as an object moves, phi can be almost anything. So what we're gonna do here, we're gonna do two things. Number one, we're gonna let phi become really small. Math speak the limit of phi as it approaches 0. We're not saying phi is equal to 0, we're just saying phi is incredibly tiny. So phi is tiny. The other bit is we need to talk about radians. And I can never remember which groups I've done the radiant bit with or not. So I'll start out with a question I usually do. Why are there 360 degrees in a circle?
Yeah, you asked us that before.
I did, okay, so I have gone through this.
Not to say I remember the answer, but you did.
Yeah, I was about to say, I don't remember.
Wasn't it?
It was because of some weird history thing, wasn't
Yeah.
it?
Well, this
Was
is just the
it
circumference.
I think it was a Roman thing.
Not a pre-Roman.
This is Greek, wasn't it?
I'd say pre-Greek too. Now we start getting into
People really long time ago just decided.
Babylonians.
Yeah, okay.
And the ideal, the perfect number of 60.
Yeah.
Okay.
Yeah, who was that decided that?
Babylonians.
Babylonians.
Whatever.
They're the ones I give credit to.
Yeah, Babylonians, we
Yeah.
have it right here.
All right, so radians was the attempt to come up with something that was more ideal, works for everything, something more natural. And so we have, for the circle, if I take a radius here and I start wrapping the radius around, so this length here is the same as the radius, that angle right there is, I'll make that theta because it's not the same as that, is 1 radian. And how many radiuses around the circumference?
2 pi.
So there's 2 pi radians in a circle. Matter of fact, there's a relationship here between what is known as the arc length and the angle. So if I have 1 radian as the angle, I have an arc length of 1 radius. 2 radians would have 2 radii, and so forth. So there's this they're directly proportional, the angle and the arc length, which can be summed up in the formula S is equal to R theta. This is the arc length. This is the radius. And this is the angle in radians. So the arc length here, this distance from here to here, that arc length is just the radius of my circle here times the angle. That angle is 2 phi. And so my arc length is R times 2 phi. But I can also find that arc length slightly differently, because it's a constant speed. That arc length, which is equal to 2 r phi, is also just equal to speed times time. So we have a way of actually getting rid of time here because we have a relationship based on the arc length, which brings in speed also, but we still run into this issue of where I have sine phi and I have a phi there. Let's go ahead and make that first substitution, and then we'll talk about how to deal with the sine phi and phi, and that gets into phi being tiny. So over here, time would be equal to 2r phi divided by v. So this becomes negative 2v sine phi j hat divided by 2r phi over V. The 2's cancel out. And that's about it. Dividing by this is the same as multiplying by the reciprocal, so we get negative V squared sine phi j hat divided by R phi. If you have your calculator and can easily put it into radians, I would suggest you do so for the moment. Don't forget to put it back to degrees when you need to. What I want you to tell me is the sine of 0.1. And then the sine of 0.01. The sine of 0.001, I'll stop it there.
So put it in radians?
Yes.
Okay.
Sine of 0.1 is 0.0998 for, yeah, just big long decimal.
Good.
It's just 0.009.
Same thing, just add
Yeah,
another zero.
yeah, move the decimal. Put a bunch of nines. And then for the last one, should be the same thing, but
But with no.
yeah.
Yeah,
Yeah, it is the same thing. Mine just gave it scientific notation, so.
Like that.
Yep.
Notice if we round off here, we get 0.1, we get 0.01, we get 0.001. This is known as the small angle approximation, which physicists love to explain when they can. If theta is much less than 1, so when you get the two less than symbols right next to each other, that means much less than, nice and specific. If theta is much less than 1, sine of theta is approximately equal to theta, which is approximately equal to the tangent of theta. It'd be really nice if I have the diagram I want. And I don't.
Well, isn't that literally just how you do a limit for a sine? Or, well, a limit in general. You just take the x value and you multiply it by, you take the equation and you put in for like 0.1 and then decrease x.
We can do something, from what you were saying, it sounds like just a straight up plug and chug and just get smaller and smaller. Yeah, the spirit of it is right. We can be a little bit more generalized than that.
Okay.
In, what do I get rid of? Get rid of this.
wait, can you say the bit about the small angle approximation again? You said that the angle is less than 1.
Much less than 1.
Is much less than 1, then,
So notice no units here, so I'm talking radians
then the sine is,
of the angle.
is approximate to the angle
Yep.
and approximate to the tangent, okay.
Yep.
Gotcha.
All right, so from a right triangle point of view, if I have some angle theta here, if theta is small, that means that my hypotenuse is practically the same length as
Okay.
the bottom here.
Yeah.
And not the way I wanted to go on that one, so. There's something known as the Mclaren series. Right? There's the Taylor series and the Mclaren series, and I sometimes get them backwards. I think it's the Mclaren series. Sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. You probably can see a pattern there. It's an infinite series, but it is possible to actually derive this if you take calculus, or when you take calculus, you'll get to that derivation at some point. If theta is small, well, a tiny number to the 7th power is almost insignificant. Matter of fact, to the 5th power is almost insignificant. To the 3rd power, probably insignificant, and so what you're just basically left with is sine theta roughly equal to whatever theta is.
Okay.
known as the first order approximation, second order approximation, if you bring that into it, and so on.
Gotcha.
So if I make phi tiny here, then my equation over here becomes negative v squared phi j hat over r phi. Now, how legitimate is it that we can make that assumption? Well, if ever I have any object that's moving in a circle, I can always take a snapshot in time where it's not going very far. I can take any point on the circle and just say, well, why don't we just look at the angles just before and just after. Because what I'm trying to figure out is what is the acceleration at a specific moment in time. Phi's cancel out, and what I'm left with is negative v squared over r j hat. So what I'm claiming here is that the acceleration, because of a change in direction, is equal to, the magnitude is equal to v squared over r in the negative j hat direction when it's here, which it means towards the middle. So a sub c, the magnitude is v squared over r, or to put it into a vector term, it is always pointing towards the middle, so it would be really convenient not to have to use j hat if I'm talking about towards the middle, because over here it's v squared over r in, well, wherever the middle is, there, that way. Down here would be that way. And we're in luck, because they have a way of writing this. We've done I hat, j hat, we go down to r hat. Now, I hat, j hat, what is considered positive depends upon what we want it to be. R hat's a little bit more restrictive. We do have a choice on what the center is, but r hat is a unit vector, thus the hat. A unit vector pointing away from the center. And since centripetal acceleration is always pointing towards the center, we do the opposite of it, which is negative. And traditionally, you put the negative in front. Negative v squared over r hat. So that's the official formula for centripetal acceleration.
So, let me just make sure I've got this straight. R hat is from the center, going away from it.
Right.
For our acceleration, we're gonna have velocity over the radius.
That is speed. Speed squared over the radius.
Squared over the radius. But in vector form, it's gonna be multiplied by the vector that we're...
Vectors have a magnitude and direction.
Right.
The magnitude is the speed squared divided by the radius.
Okay.
The direction is towards the center. The way that is generally indicated towards the center is we bring in what's called the radial unit vector.
Okay.
Throw that word in there, radial. The radial unit vector. Radial unit vector is defined to be pointing away from whatever the center is. Because centripetal acceleration points towards the center, we throw a negative in there. It just means opposite of away.
Okay.
Did I cut you off before you had finished working it out?
No, I mean, I'm just trying to understand where the difference is between the unit vector radial, the radial unit vector and R. Is R just the...
Okay. That's a unit vector, that's a radial unit vector pointing away from the center of the circle.
Right.
That's just the radius of the circle.
Okay. Okay.
Yeah, this is not the magnitude of that.
Okay. Is
Because
that
that kind of consistency would just be crazy.
Yeah. Is that just a general formula of what we're gonna be using for centripetal force?
Yeah, or, yes.
Okay.
Centripetal force would be mass times that.
Okay.
Any questions before I start erasing stuff?
I do have another question.
Okay.
So with arc length, you said 2r5 is also equal to velocity times time.
Speed times time.
Speed times time. Where did you come up with the speed times time equaling that?
I have an object traveling at a constant speed.
Right.
So it doesn't matter what the path is, if I know how much, if I'm traveling at a constant speed for a certain amount of time, I just multiply the two to get to how far I've gone.
Okay.
So traveling 50 miles per hour for 3 hours, I'm gonna go 150 miles.
Okay.
So that's where that comes from. The direction is changing, but that's why I multiply by speed, not velocity. So I multiply by the speed of, then that tells me how far I've just traveled from here to here.
Okay. Which is also, okay, equal to arc length.
Yes.
So our final answer is that?
Yes.
So what's the question?
Ultimately, what is the acceleration of an object that is changing directions? Because up till now, we dealt with acceleration because of change in speed. Now we're adding in change in direction.
Why is it changing directions in like circle way?
Remember when I was spinning the thing around in the class?
Is
Pardon?
that the same question with the spin?
It is, because if this is sort of overhead view, I'm spinning this, and if I let go when it's here, that thing's gonna go in that direction. Because objects wanna keep doing whatever it's doing. If I let go of it here, it's gonna go in that direction. So what that's telling me is that the direction of the velocity is that way here, it's that way there. So the direction changes. Did I answer what you were asking?
Yeah.
Okay.
Yeah, if direction is changing but speed is staying constant, the only possible answer is for it to be traveling in a circle, right? Well, is it acceleration? Okay. Like, yeah, if your speed is constant but your direction is constantly changing. It doesn't have to be.
It doesn't have to be a
It
circle.
could be like a,
Yes.
the sine wave or something.
You put your car on cruise control and.
See what happens,
zip around.
yeah.